Mercury, an enigmatic planet, despite being closest to the Sun, is still the least known to us. Often overshadowed by its neighbors, it's a world of mystery waiting to be revealed. What if Mercury isn't what we thought it was? Recent discoveries indicate that this planet is more dynamic and complex than anyone imagined. From shrinking landscapes to mysterious blue troughs, Mercury is challenging everything we know about it. Imagine a planet rushing around the Sun at breakneck speed, a world so close to the solar furnace that it's hard to even get close to it. Few missions have dared to visit this elusive world, and those that have discovered only glimpses of its secrets. However, a new mission, Bepi Colombo, is on its way, and it promises to unlock mysteries that have puzzled scientists for decades. Already we're seeing things that defy explanation: strange features, unexpected phenomena, and hints of a story yet to be told. Mercury's X-ray auroras, its changing topography, and its hidden interior all suggest that the planet is far more intriguing than we ever thought. Prepare to see Mercury in a whole new light. It's not just a planet, it's a mystery at the edge of the Sun. Mercury, the innermost planet, orbits closest to the Sun. It's the smallest planet, slightly larger than our Moon, and takes only 88 Earth days to complete one orbit. Because of its proximity to the Sun, Mercury experiences temperature extremes that range from scorching highs of 800 degrees Fahrenheit to an icy low of negative 290 degrees Fahrenheit overnight. Its surface is a mosaic of craters, ridges, and plains. Unlike other planets, it has no significant atmosphere to protect it from meteoroids, resulting in a landscape heavily riddled with craters and reminiscent of our Moon. One of the most striking features is the Caloris Basin, one of the largest impact craters in the solar system. This massive basin, about 960 miles in diameter, was formed by a colossal impact early in Mercury's history. Another unique aspect of Mercury is its unusually large core, which makes up about 85% of the planet's radius. This iron-rich core generates a magnetic field, but it's only 1% as strong as Earth's. Despite its weak magnetic field, Mercury has magnetic poles and a magnetosphere that interacts with the solar wind, creating phenomena such as the recently discovered X-ray auroras. Exploring Mercury presents significant challenges. Mercury's proximity to the Sun means that spacecraft must withstand intense solar radiation and heating. In addition, Mercury's fast orbit requires precise and energy-intensive maneuvers to enter its orbit. In 1973, NASA launched Mariner 10, the first spacecraft to visit Mercury. Mariner 10 utilized the gravitational assistance of Venus, allowing it to make 3 flybys of Mercury between 1974 and 1975. These flybys produced the first close-up images of the planet's surface, showing the planet's heavily cratered terrain and complex geologic features. The spacecraft's images showed a world similar to our Moon, with vast plains and numerous impact craters. However, the mission captured only 45% of the planet's surface, leaving much unexplored. Despite the limited coverage, the mission data laid the groundwork for future research. Decades later, the Messenger spacecraft launched by NASA in 2004 became the first spacecraft to orbit Mercury. After a challenging journey that included flybys of Earth, Venus, and Mercury itself, the spacecraft entered its target orbit in 2011. During its 4-year mission, Messenger made more than 4,000 revolutions around the planet, collecting a wealth of data on the planet's surface, composition, and magnetic field. MESSENGER showed Mercury's surface in unprecedented detail, mapping almost the entire planet. It revealed volcanic plains, evidence of past tectonic activity, and gave a glimpse of the planet's thin exosphere. One of the most surprising discoveries was the presence of water ice in permanently shadowed craters at Mercury's poles, even though the planet is close to the Sun. Building on the successes of Mariner 10 and MESSENGER, the Bepi-Colombo mission represents a significant step forward in Mercury exploration. The mission is a joint effort between the European Space Agency and the Japan Aerospace Exploration Agency. Launched in 2018, Bepi-Colombo should provide comprehensive data on the geology, atmosphere, magnetosphere, and history of Mercury. Bepi-Colombo consists of two main spacecraft, ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter, also known as MEA. Together, these spacecraft will study the planet from different perspectives, offering holistic views of its evolution and environment. The mission's journey to Mercury will be long and complex, involving many gravity assist systems. Bepi-Colombo has already made flybys of Earth in 2020 and Venus in 2020 and 2021. It'll make 6 flybys to Mercury before entering orbit in December 2025. These flybys are critical to adjust the spacecraft's trajectory and slow it down enough to be captured by Mercury's gravity. The goals of Bepi-Colombo are ambitious. The mission should map the planet's surface in high resolution, analyze its composition, and study the magnetic field and magnetosphere. It will also study the planet's exosphere and search for evidence of past volcanic and tectonic activity. By comparing data from both orbiters, scientists hope to gain new insights into the formation and evolution of Mercury as well as its mysterious magnetic field. So, since its launch in 2018, Bepi-Colombo has been steadily approaching Mercury, making a series of flybys that have already yielded significant results. These preliminary observations provide new insights into Mercury's complex geology and dynamic environment. One of the key contributions of the mission was the detailed mapping of Mercury's surface. The spacecraft discovered many previously unknown craters, each telling a different story of the planet's turbulent history. Among them are impact basins that show the scars of ancient collisions, shedding light on the early chaotic period of the solar system. One of the mission's most intriguing discoveries is the detection of X-ray auroras around the planet. Unlike visible terrestrial auroras, Mercury's auroras are detected in the X-ray spectrum. This phenomenon was first hinted at by the MESSENGER mission and is now confirmed by Bepi-Colombo. These X-ray auroras are caused by the interaction between Mercury's magnetic field and the solar wind, a stream of charged particles emitted by the Sun. When these particles collide with the planet's surface, they generate X-rays, causing a faint but scientifically valuable glow. This discovery not only confirms the presence of a magnetosphere, but also provides insight into the nature of Mercury's magnetic field and its interaction with the solar wind. Another important recent discovery was confirmation that Mercury continues to shrink. High-resolution images have revealed features such as lobate scarps and wrinkle ridges, which are formed by the compression of the planet's crust as its core cools and hardens. These results build on observations made by the MESSENGER mission and provide clearer evidence of Mercury's ongoing geologic activity. The planet's compression has caused its radius to shrink by several kilometers since its formation, creating stress cracks on the surface that manifest themselves as ridges and cliffs. Bepi-Colombo, in turn, has identified several regions where this contraction is most obvious, providing a unique opportunity to study planetary geology in real time. These regions reveal not only Mercury's cooling history, but also its current state, giving scientists clues about the planet's internal structure and thermal evolution. At first glance, Mercury's heavily cratered surface resembles that of our Moon, Both bodies are riddled with impact craters, indicating a long history of collisions with asteroids and comets. However, a closer look reveals significant differences. Mercury's craters are often interspersed with ridges and fault scars, which are less common on the Moon. These scars are indicative of Mercury's compression, a process not observed on the Moon. In addition, there are areas on Mercury's surface with fewer boulders than on the Moon, suggesting different geologic processes. One of Mercury's most enigmatic features is its depressions. First discovered by the MESSENGER mission, they're irregular, shallow depressions, often surrounded by bright halos. Their formation has puzzled scientists since their discovery. Initially, the researchers hypothesized that these depressions might be of volcanic origin. They considered the possibility that volcanic processes had left behind these unusual formations. However, the distinct appearance of the depressions and the lack of associated volcanic features prompted further investigation. According to the current thinking, Mercury's troughs were formed by sublimation, a process by which solid materials are converted directly into gas. This process probably involves volatiles beneath Mercury's surface. When these volatiles sublimate, the surface erodes, forming sinkholes and bright halos that are seen around the depressions. These data suggest that despite its proximity to the Sun, Mercury stores volatile compounds just beneath its surface. Continued sublimation and the formation of depressions indicate the planet still is a geologically active world, contrary to previous belief. Mercury's proximity to the Sun and the extreme temperatures of its surface led scientists to believe that it was devoid of volatile compounds. However, recent discoveries have dramatically changed this view. High concentrations of sulfur, chlorine, sodium, and potassium have been found on Mercury's surface, indicating the presence of volatile-rich layers extending several kilometers deep. The discovery of sublimation depressions with a flat bottom and a bright interior and halo, indicates the existence of volatiles beneath Mercury's surface. These depressions form when volatile materials sublimate, causing the surface to erode into sinkholes. This ongoing geologic process suggests that Mercury is still losing volatiles, which changes our understanding of its geologic history and activity. Sublimation leads to another very fascinating event occurring on the planet, its sodium tail. Observations have shown that Mercury emits a tail of sodium atoms, making it, in a sense, similar to a comet. This phenomenon is caused by solar radiation and solar wind throwing sodium atoms from Mercury's surface into space. The sodium tail extends millions of miles into space and is a clear indicator of the ongoing release of volatiles from the planet's surface. The tail is not visible to the naked eye, but can be detected with specialized instruments, allowing us to learn much more about Mercury's exosphere and the processes that contribute to its formation. Interestingly, the volatile content of Mercury has been compared to some of the most extreme environments on Earth, such as the Atacama Desert in Chile. Both regions have high concentrations of salts and other volatiles, despite very different environmental conditions. The Atacama Desert is known for its extremely dry condition and high salt content, which supports unique extremophiles, organisms that thrive in extreme conditions. Research suggests that similar conditions may exist beneath the surface of Mercury, where salts and other volatiles can create niches for potential microbial life, albeit under much more extreme conditions. Extremophiles in the Atacama Desert survive in highly saline and dry conditions, suggesting parallels with potential habitats on Mercury. These microorganisms have adapted to live in niches with minimal water and high salt concentrations, suggesting that life could potentially exist in similar conditions on Mercury. If Mercury has a volatile-rich subsurface, It's also possible that this environment could provide the necessary conditions for life, at least in microbial form. The presence of halides and other salts could lead to the formation of liquid water through a process of deliquescence, where salt absorbs moisture from the atmosphere, even in small amounts, potentially supporting microbial communities. The origin of mercury has long puzzled scientists. According to traditional theories, it formed not far from its current position. However, a considerable amount of recent research agrees that mercury could have started its journey much farther from the Sun. One of the leading theories is planetary migration, where early in the history of the solar system, gravitational interactions caused significant shifts in planetary orbits. Mercury could have been formed in the outer region of the solar system, rich in volatile matter, and migrated inward over time. Evidence in favor of this theory comes from Mercury's unusual density and its large, iron-rich core. According to recent studies, Mercury's core is about 85% of its radius, which is much larger than any other terrestrial planet. Some scientists speculate that Mercury was once a much larger planet, similar in size to Mars, with a thick mantle and crust. A catastrophic collision with another large body could have stripped Mercury of most of its outer layers, leaving behind a dense core and thin mantle. This hypothesis explains Mercury's high density and the presence of high levels of some elements, such as thorium and potassium, that are commonly found deep in planetary interiors. The giant impact theory is supported by Mercury's geologic features. The planet's surface is marked by impact craters and basins, such as the Caloris Basin, one of the largest impact structures in the solar system. This collision theory is consistent with observations of other celestial bodies and their histories. Similar collisions are thought to have led to the formation of the Moon and caused significant changes in other planets, suggesting that Mercury's history may be part of a larger pattern of planetary evolution in the solar system. The discovery of bainite, a rare type of volcanic rock on Mercury, is also intriguing evidence. Bainite is typically rich in magnesium and low in other elements, indicating that it formed under special conditions associated with high temperatures and pressures. Geologists have found similar rocks in Cyprus, suggesting a common formation process. They appear white in the images because bainite oxidizes in Earth's oxygen-rich environment. These terrestrial analogs provide insight into Mercury's volcanic history and support the idea that its mantle has undergone significant melting and differentiation. On Cyprus, bainite is associated with ancient tectonic processes when the oceanic crust was pushed deep into the mantle and partially melted. The presence of similar rocks on Mercury suggests that it too has undergone intense geologic processes, possibly related to a hypothetical major collision and subsequent migration. By comparing geologic formations on Mercury with those on Earth, scientists can piece together the story of Mercury's formation and evolution. Features such as fault lines, ridges, and volcanic plains on Mercury resemble those found in tectonically active regions on Earth. These comparisons show that despite its small size and proximity to the Sun, Mercury has a dynamic and complex geologic history. Studying Mercury's geology not only helps us understand its past, but also provides insight into the processes that have shaped other rocky planets in our solar system. As Bepi Colombo approaches its destination, scientists are looking forward to the vast amount of data it will provide. The mission is expected to provide detailed maps of Mercury's surface, study its magnetic field, and provide new information about its geologic history. Although the search for life on Mercury is unlikely, the discovery of volatiles and potential subsurface environments offer intriguing possibilities. Extremophiles on Earth thrive in harsh environments, suggesting that similar life forms could exist on Mercury given the right conditions. Mercury occupies a unique place in planetary science. In the broader context of solar system studies, this planet serves as a key to unraveling the history and evolution of the terrestrial planets. Its study helps us understand the processes that have shaped not only our solar system, but perhaps the rest of the solar systems as well. As we look forward to the next wave of discoveries, Mercury promises to remain the center of scientific inquiry, offering endless opportunities